Welcome. So the topic we'll be discussing in this lecture is mapping functions. So, we are discussing about memory subsystem, and especially in memory subsystem we are discussing about cache memory. So in the last class we have discussed that cache memory basically works on the principle of locality of reference, and there were two types of locality of reference, like temporal locality of reference, spatial locality of reference, and also we have discussed what is a cache hit, what is a cache miss, and also we have discussed what will happen when there is a read hit and read miss, and what will happen when there is a write hit and write miss. Okay, so in that process we have also understood that the memory will be divided into several blocks. Okay, and few blocks will be available in the cache memory, because the size of the cache memory is limited. We don't have a very huge cache memory size, so only some blocks of the main memory will be available in the cache memory. Okay, so we need a mapping function to map between the main memory and cache memory, like which blocks of the main memory are currently available in the cache memory, right? So that is the objective of this lecture. Okay, say for example this is the main memory. Okay, say that main memory contains many blocks. Okay, a block is nothing but a collection of words. A block is nothing but a collection of words. Assume that main memory contains 4096 blocks. 4096 blocks. Okay, and each block contains several words, maybe 8 words or 16 words or 32 words, that depends. Okay, say this is the cache memory. Assume that the cache memory can hold maximum 128 blocks, 0 to 127, that is, it can hold maximum 128 blocks. Then at any time cache memory can hold any of these 128 blocks. Okay, that is, from the main memory you have 4096 blocks. Out of these 4096 blocks, it can hold any 128 blocks. Okay, 0 to 127, that is 128 blocks. Okay, whether this block is it currently here or not, whether this block is here or not, which block of main memory is available in the cache memory, we need an understanding of that, and that is achieved through what is called as mapping functions. Okay, and how that mapping is getting done, and what are the different ways of doing that mapping, that's what the objective of this particular lecture. Okay, fine, let us start. So basically the mapping function determines how memory blocks, I mean the memory blocks in the main memory are associated with the respective memory blocks in the cache memory. What is the relationship between the memory blocks of the main memory and that of the cache memory? That is what the mapping function does. Okay, so let us try to understand mapping function with a simple example. Okay, let us consider this particular example. Let us assume that the cache memory consists of 128 blocks. Okay, so we have a cache memory. So in the system we have a cache memory, and the cache memory can maximum hold 128 blocks. Okay, that is block 0 to block 127 it can hold, right? And each block can contain 16 words. Each block can contain 16 words. Okay, so totally, okay, each block can contain 16 words. The size of the word varies with computer to computer. It can be either 1 byte or 2 byte or 4 bytes, whatever it may be. We are not going into that. Okay, so only thing we know that the cache memory can hold 128 blocks, where each block can hold 16 words. Okay, so totally cache memory can hold how many words? That is, it is 16 into 128, that many words it can hold. Okay, 16, because there are totally 128 blocks and each block can hold 16 words. So totally cache memory can hold how many words? It can hold this many words, 2048 words. Okay, that is 2 kilo words. 2k, 2048 is nothing but 2k. 2k words. We are saying 2k words, we are not saying 2k bytes or whatever it may be, because we don't know what is the word size. Okay, word size may be either 16 bit or 32 bits or whatever it may be. So we just say that it can hold 2k words, right? Okay, So this is what we assume about our cache memory. Okay, now what is our assumption about the main memory? Let us assume that main memory is addressable by 16-bit address. Okay, to address the main memory we are using 16 bits. That is fine. And main memory has 64k words. Main memory has 64k words. Okay, that is, or you can also call 64k blocks. Main memory has main memory has 64k words. uh, First let us not see this, first see this point. Main memory has 4k blocks. Main memory has 4k blocks and each block can hold 16 words. Okay, right? So so what we what so 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 the point is, cache memory contains how many blocks? 128 blocks, and each block contains how many words? 16 words. Okay, so this is what our assumption about the cache memory. Okay, for the example that we are uh, going to discuss. Okay, with this example only we are going to understand the mapping function, right? And coming to main memory, so main memory, what we assume in the sense, main memory contains 4000 blocks. Okay, 4k blocks. Okay, so what is 4k? 4k means 4 into 1024. Okay, 1k, one normally kilobyte or whatever kilo in computer science, it is not 1000, it is 1024. Okay, so it is 4k, means 4 into 1024, which is 4096 blocks. Okay, so main memory contains this many blocks, 4k blocks, that is, it contains 4096 blocks. Is it clear? So from block 0 to 4095 blocks it contains, totally 4096. Okay, the numbering is from 0 to 95, the numbering is from 0 to 95, but the total is 4096 blocks. Okay, where again each block can hold 16 words. Each block can hold 16 words. Okay, so totally how many words the main memory can hold? It is 4096 into 16. Okay, 4096 into 16, what is that? That is nothing but 65,536 words. Okay, that is nothing but 65,536 words. This many words it can hold. Okay, this many words it can hold, right? So this is nothing but 65,536 is, now you see this, 65,536 is nothing but 64k kilowords. 65,536 is nothing but 64k kilowords. Okay, so how, let us check. So you just remember this 65,536. Now let me multiply 64k, that is into 1024. So what you get? 65,536. Okay, so that is how we got this 64k. Okay, right? So only thing you have to remember that the size of the cache memory is 128 blocks, where each block can hold 16 words. The size of the main memory is, that is, main memory can hold 4k blocks, that is 4096 block, where each block can hold 16 words. Okay, so 4000 into 4096 into 16 words is, totally it can hold 64k words, that is 65,536 words. Okay, this many words can be stored in the main memory. 65,536 words can be stored in the main memory. Okay, where totally it contains 4096 blocks and each block contains 16 words, whereas cache memory can hold totally 2048 words. Okay, and it contains 128 blocks and each block contains 16 words, right? Fine. So with this introduction, let us jump into the topic. Okay, so there are three types of, basically there are three mapping functions we are going to discuss. The way in which the main memory and cache can be mapped can be done in three ways. Okay, so what are the three ways? That is what we are going to discuss in this lecture. So the first method of mapping is called as direct mapping. The second method of mapping is called as associative mapping, and the third method of mapping is called as set associative mapping. Okay, here the third method is nothing but it is a combination of first two methods. Okay, The first method is direct mapping, second is associative mapping, and the third is set associative mapping. Okay. So how these mapping techniques works, let us try to understand. So first let us start with direct mapping. First let us start with direct mapping. Okay. So this is the main memory. As we have discussed, main memory contains how many blocks? Block 0 to block 4095. And what is the size of the each block? Each block can hold 16 words. Each block can hold 16 words. Okay. And what is the size of the cache memory? Cache memory can hold 128 blocks. Block 0 to block 127. Again here each block can hold 16 words. Okay, this is the scenario, right? Now if you see the cache memory, it is only 128 block. It has only 128 blocks, but the main memory has 4096 block. Okay, so at a given time in a cache memory, you can keep any of these 128 blocks. That's all. At a given time in the cache memory, you can keep any of these 128 blocks out of this 4096 block. Okay, from this 4096 block, any of these 128 blocks can be mapped into the cache memory. Now how the direct mapping is going to do that? That is the question. Okay, so the logic or the concept that is followed by direct mapping is very simple. What it does in the sense, whenever it want to map any of the memory block from main memory to cache memory, what it does in the sense, it just takes the block number of the main memory, block number of the main memory, okay, and it performs modulo division, with the total number of blocks, that is with the maximum blocks available in the cache memory. So cache memory supports how many blocks totally? 128. Cache memory supports only 128 blocks. So it just performs the block number of the main memory modulo 128. What is the result? 0 modulo 128 is 0. It means that if at all this block should be moved to the cache memory, it will be moved and kept only in block 0. Are you getting? If at all block 0 is to be moved to the main memory, cache memory, it will be moved, a copy will be moved and it will be kept only in block 0 of the cache memory. It will not be kept in any other blocks. Is it clear? So that is the point. Okay. Similarly, if you want to move block 1, then again you perform 1 modulo 128. So which is nothing but 1. Okay. That is block 1 of the main memory. If it is to be moved to the cache memory, it will be moved only to block 1. Okay. So on and so forth. So this will continue up to what? Up to block 127. Okay. Block 2 of main memory will go only to block 2 of cache memory. Block 3 of main memory will go only to block 3 of cache memory, and so on and so forth. This process will continue up to 127. Block 127 of main memory will go to which block of cache memory? 127 modulo 128 is 127 modulo 128 is again 127. It will just go to the 127th block of the cache memory. Okay, right? Now the next cycle starts. The block 128 of main memory, where it will go? Block 128 of main memory, where it will go? Modulo 128 is what? Modulo 128 is what? 0. This will also go to block 0. Are you getting? And block 129 will go to which block? Block 129 modulo 128 is what? 1. This will also go to block 1. Okay. Block 130 modulo 128, where it will go? It will go to block 2. It will go to block 2. Okay. So the point I am trying to say is, not only one block of the main memory will be matched to the respective block in the cache memory. No, many blocks of main memory will be mapped to the same block of the cache memory. For example, if you take block 0, block 128. Okay. Next, if you take block 256, okay, block 0, block 128, block 256. What else? 256 plus 128 is how many? That is all multiples of 128 will map to all multiples of 128 will map to block 0. Okay, so right, So 128 into 2 is 256. Okay, 128 into 3 is what? 128 into 3 is 384. So block 384, 128 into 4, that block, all these blocks will map to which block? It will map to block 0. All these will map to block 0. 128 also maps to block 0. Right? Are you getting? Block 0 also will map to block 0. Okay. Similarly, if you take block 1, it maps to block 1, and block 129 also maps to block 1. Okay. How you 1 plus 128 is 129. Okay. Similarly, 129 plus 128 is what? 129 plus 128. So that block also will map to block 1. 129 plus 128. What you get? 257. Block 257, where it will map? It will also map to block 1 of the cache memory. Okay. Again 257. If you do 257 plus 128, 257 plus 120. Sorry. 257 plus 128, which is 385. Block 385 will also map to block 1. Okay, right? So the point is, multiple blocks of main memory will map to the same block of the cache memory. Multiple blocks of main memory will map to the same block of cache memory. Okay, so this is how the direct mapping technique works. The advantage of the direct mapping technique is it is very simple. Okay, it is very simple. The logic or implementing this is very simple. Okay, but the disadvantage is it is not flexible. Why it is not flexible? This is the reason, because more than one block of the main memory will map to the same block of the cache memory only. It will not map to any other blocks. Okay, assume that in a given situation, I will give one scenario. Say that cache memory is totally empty. You are not at all using any blocks. Okay, assume all these 128 blocks are empty. Okay, assume all these 128 blocks are empty, right? Now say that processor want to move, processor or the memory circuit or whatever you call, the memory circuit want to move say 5 blocks from the cache memory to, from the main memory to cache memory. 5 blocks, just 5 blocks should be moved from main memory to cache memory. So cache memory is totally free. There are sufficient space available in the cache memory. Okay, but still you may face a problem because of this issue, because multiple blocks of main memory are mapping to the same block of the cache memory. Okay, say for example these 5 blocks, which 5 blocks the processor wants, in the sense, say processor want to load block 0 of main memory, again block 256 of main memory, okay, and say block 129 of main memory, okay, and say some other block, say that is something different, say block 10 of the main memory. Okay, so how many? 4, and say block 12 of the main memory, from the main memory. Okay, now what will happen? Block 10 of the main memory will go to block 10 of the cache memory, right? Block 10 of the cache memory, right? Block 12 of the main memory will go to block 12 of the cache memory. That is fine. Up to this it is fine. But what about block 1 of the block 129 of the main memory will go to block 1 of the cache memory. That will go to block 1. Okay, that is also fine. Okay, now say block 0 of the main memory will go to block 0 of the cache memory. Okay, now where will this block 256 should go? Block 256 also should go to block 0. Block 256 also should go to block 0. It cannot take any other blocks. Okay, it cannot take any other blocks. But is there sufficient space in the cache memory? Yes, there are many spaces, but still 256 cannot use those space. This particular block 256 of main memory, it cannot use those empty space. It should be kept only in block 0 of the cache memory. Okay, so this is a restriction. So this is the problem with direct mapping. It is less flexible. Okay, the problem with direct mapping is it is less flexible. It is not flexible. That is, say here I want to move this block 256, but block 0 is not free. Block 0 is already occupied by some other block. So can I keep this 256 in some other empty block, of the cache memory if there is an empty block available? No, you cannot keep. That is what the direct mapping concept says. That is what the direct mapping concept says. Okay. So then when can you load 256? You can load 256 only if you replace this block 0. Okay, for that you have to apply the replacement algorithm. Then once the processor finished using this block 0, then it should be replaced. Then after removing this only, the 256 can come. Is it clear? So this is the drawback with direct mapping, right? So with direct mapping, more than one block of the main memory will be mapped to the same block of the cache memory. So in such cases, if you want to move multiple blocks from the main memory, which refers to the same block of the cache memory, then only one of such blocks can be moved. The other blocks cannot be moved, and they have to be later at a point of time they have to be replaced. And this will happen even if there is sufficient space in the cache memory. Okay, even if there is sufficient empty space in the cache memory, those two blocks which are referring to the or which are mapping to the same block of the cache memory cannot be brought into the cache memory simultaneously, right? So this is the drawback with the direct mapping techniques. Okay, so this is whatever we have discussed. Block J of the main memory maps to J modulo 128 of cache, that is 0 maps to 0. Okay, that is block 0 maps to 0. Okay, 129 maps to 1, so on and so forth. Okay, right? More than one memory block is mapped onto the same position or the same block in the cache. That is a drawback. Okay, so this will lead to contention for cache blocks even if the cache is not full. Contention means competing for a block. Okay, in this case if you see, if the main memory block 0 also will compete for block 0 of cache, and main memory block 256 also will compete for block 0 of cache memory. Okay, that is called as contention. Okay, the block 0 of the main memory also will compete for block 0 of the cache. Block 256 of main memory also will compete for block 0 of cache. Block 120 or 128 of main memory also will compete for block 0 of cache. Okay, that is called as this problem is called as contention. Okay, so this may lead to contention even if the cache is not full. Okay, even though the cache is not full, there will be contention. I mean, multiple blocks of the main memory may be competing for a particular block in the cache memory. Okay, even though there are other empty spaces, they cannot take those spaces. Right? Fine. To resolve the contention, we have to go for replacement algorithm. Right? Okay. Fine. So this is the brief overview about direct mapping. And one more thing, for direct mapping, the addressing used to refer the main memory is, processor will generate an address that refers to the main memory, right? Then the memory circuit can use that to, by using that address, it may check whether the data is available in the cache or not. Okay, if it is available in the cache, it will get from cache, otherwise it will fetch from main memory. Okay, that is the normal point, but processor will generate always an address that refers to the main memory. Okay, so the address which is used by direct mapping, actually it contains totally 16 bits. Okay, in our example it contains 16 bits. Okay, out of these 16 bits, the last 4 bits, that is the least significant 4 bits, will refer to a particular word, because in each block there can be how many words? 16 words will be there. Okay, so these 16 words, to refer these 16 words, we need 4 bits. Okay, 2 to the power 4 is nothing but 16. Okay, so the least significant 4 bits are used to refer to the specific 16 words, which word we are going to currently access, right? The next 7 bits will refer to the actual block number. The next 7 bits will refer to the particular block number. Okay, the particular block number. Okay, that is that in the sense that totally you have how many blocks in the I mean, totally we have how many blocks in the cache memory? Totally we have how many blocks in the cache memory? We have 128 blocks. Okay, we have 128 blocks in the cache memory, right? So to address these 128 blocks, we need 7 bits. 2 power 7 is nothing but 128. 2 power 7 is nothing but 128. Okay. So this will refer the respective block number. Okay. This will refer to the respective block number, whether it is block 0 or block 1 or block 2 or block 3 up to block 128 it will refer. Is it clear? Okay. And the last thing, this what is this last bit, the most significant 5 bit. Okay, so this will actually refer to the this will refer to uh, this will refer to what, in the sense, see see here, if you see uh, this last 5 bits, actually it refers to like which set of 128 blocks is currently available in the cache. Is it clear? Which set of 128 blocks is currently available in the cache? That will be referred by these last 5 bits. Okay. So how many such 128 we have? How many such 128 blocks we have? See, for example, the main memory contains how many blocks? 4096 blocks, and cache can hold how many blocks? 128 blocks. Okay. So what is the total combination we have? So some set of 128 blocks, maximum some set of 128 blocks can be available in the cache at a given time. Okay, so this is one set. Maybe it need not be sequential, it can be any combination, right? So which set is available? So that is represented by the last 5 bits. So you may ask, why last 5 bits? So totally how many how many blocks are there in the main memory? 4096 blocks, and cache can accommodate how many blocks at a given time? 128 blocks. Okay, so 4096 by 128 is how many? 32 blocks. Okay, 32. Okay, that is 32 sequence or 32 combinations of 128 blocks can be available in the cache at a given time. Okay, so that 32 combination can be anything. It can be first 32 or middle 32 or last 32 or any random 32. For example, block 0, block 129, block 255, block any combination of 32 can be available in the what you call cache memory at a given time. Okay, so that is represented to the last 5 bits. Okay, so the last 5 bits says that whether a particular 32 whether a particular block from the main memory is currently in the cache or not. Okay, whether a particular block from the main memory is currently in the cache or not, that is identified through this last 5 bits. Okay, right. Fine. So this is about direct mapping. So whatever we have discussed, it was explained here. The lower order 4 bits determine the 16 words, and the next 7 bits determine which block is in the cache, and the higher order 5 bits determine which of the possible 32 blocks is currently present in the cache. Okay, so any 32 sequence of blocks can be in the cache memory, right? 128 blocks can be there, but from 4096 it can be of any of the sequence, right? So which sequence, that is identified by this last 5 bits. Okay, fine. So these last 5 bits are also called as tag bits. These last 5 bits are also called as tag bits. Okay, so the problem with the direct mapping is it is less flexible. It is simple to implement, but they are not flexible. Okay, so that's the reason we are going for the next type of mapping, which is called as associative mapping. So the second type of mapping is called as associative mapping. Okay, so in associative mapping, what we do is we don't what you call we don't divide the block number by 128 or anything. We don't do such things. Okay, rather what we do in the sense, what we say in the sense, any block of the main memory can be placed in any empty block of the cache. That's all. It is as simple as that. Any block of the main memory can be kept in any empty block of the cache memory. There is no need to check anything. You want to move, say processor needs block 256, currently it is not in the cache, identify any empty block in the cache and just move that to the cache. That's all. Okay, so here how addressing is done in the sense, again here we have 16 bits. the least significant 4 bits will refer the to that particular word. Okay, because I mean to the particular word, because each block contains 16 words. Okay, so the specific words are individually addressed using the last 4 bits. Okay, the remaining 12 bits are used to identify the particular block number. Okay, the remaining 12 bits are used to identify the particular block number. Okay, so any block can be kept in any empty location in the cache. Okay, so using 12 bits you can address how many blocks so using 12 bits you can address how many blocks. You can address 2 to the power 12 blocks. Okay, so that is 2 to the power 12, which is nothing but 4096. Okay, that is any of these blocks you can address. Okay, so any of these blocks can be kept here, right? So if you want to move this block to 55, you identify an empty block and keep it here. Okay, and this tag bit, this is block 255, no, so this tag bit should be set according to the 255 value. Okay, so 255 means what? 255 means I think the least significant 7 bits should be 1. All the last 7 bits should be 1. That is 255. Are you getting? So the point here is any block of the main memory can be placed in any empty block of the cache memory, and the most significant 12 bits are used to refer to the particular block number of the main memory. Okay. After moving to the cache memory, also you should know. This block belongs to the which block of the main memory. Okay. For that only this tag is being used, right? Okay. But here, so this is when compared with direct mapping, this is more flexible. Okay. That is the advantage of this technique. It is more flexible and uses cache space efficiently, but still it has a drawback. Okay, and another advantage is replacement algorithm can be used to replace any existing block. Okay, so here replacement comes only when the cache is full. If the cache is full, you can replace any of the block which you want to empty out. Okay, if you feel that some block is not being used by the processor for a long period of time, move that block to the main memory and bring the new block here, right? Okay, but the drawback with this technique is, say for example, processor wants to access a particular block. Say processor want to access this block 1022, this block processor want to access. Now the memory circuitry, first it has to check whether this block is available in the cache memory or not. For this, the memory circuitry has to perform how many comparisons, it has to actually perform 128 comparisons. It has to compare everything. Most case it has to compare everything. It has to compare every tag, whether the tag is equal to this particular block or not. Only then it can confirm that it is available or not available. Are you getting? So this is the drawback. The cost is higher than direct mapped cache because it need to search all 128 patterns to determine whether a given block is in the cache or not. Okay, so it has to compare all the 128 blocks to check whether a particular block is in the cache memory or not, right? So this is the drawback with this particular technique. Okay, fine. So next we are going for a third technique, which is called as set associative mapping. So set associative mapping, basically it is a combination of two things. It is a combination of direct mapping and associative mapping. Okay, how is that? Let us see. Okay, so here we are using a new term called set. What is a set? First let us try to understand what is a set. Okay, so so previously we used the term called block. What is a block? Block is a collection of words. Okay, block is a collection of words. Okay, set of words we call it as blocks. Collection of words. I say just W. Okay. Now what is a set? Set is a collection of block. That's it. What is a set? Set is a collection of blocks. Okay. So one or more blocks we put together, call it as a set. Okay. So here we are going to create something called a set. Blocks of cache are grouped into set. Okay, there is blocks of cache memory. Okay, it is not in the main memory. So more than one block of a cache memory is grouped to form a set. Okay, It's not necessarily more than one or more than one. Okay, right? So as a simple case, let us assume that two blocks form a set. Okay, so block 0 and block 1, it becomes set 0. Okay, block 2 and block 3, it becomes set 1. Okay, block 4 and block 5, it becomes set 2, so on and so forth. Like that we form multiple sets. Okay, then what we do, the mapping function, what it will do in the sense, it allows a block of the main memory. The mapping function allows a block of the main memory to reside in any block of a specific set. What does it mean? See, let us take this example itself. In this example, how many blocks are there? 128 blocks are there. Okay, there are 128 blocks. 128 blocks. Okay, now we are grouping this into sets. How we are grouping? Two blocks will form one set. Okay, every consecutive two blocks will form one set. Okay, so totally there will be how many sets will be available here? Totally how many sets will be available here? 128 blocks means there will be totally 0 to 63 sets. That is nothing but 64 sets will be available, right? 64 sets will be available. Okay, totally we will have 64 sets, right? Okay, now when you want to move any particular block to the cache memory, what you have to do is you take that block number. Okay, you take that block number and divide it by, okay, and divide it by 64. Okay, previously we have divided by, previously what we did, we have divided by 128, right? In case of direct mapping, we have divided it by 128. Okay, now you divide it by 64. Okay, so when you divide 0, I mean modulo division, when you perform 0 modulo 64, what will you get? 0. Now this 0 represents set, so this, it means that block 0 can go to set 0. Block 0 can go to set 0. In set 0, it can go to any block. Our case, set 0 contains how many blocks? 2 blocks. So it can go to either block 0 or block 1. Okay, let us assume that it has gone to block 1, so it is occupied, right? Okay, now if you want to similarly move block 1 of the main memory, again modulo divide by the number of sets. Totally we have how many sets? 64 sets. So when you perform 1 modulo 64, what you get is 1. It means that block 1 can go to first set. Again, first set, there are 2 blocks are there, so it can take any block. Let us assume it has taken this block, right? Okay, say like that we are allocating blocks or sets for a particular block, right? Now assume that finally 128, the block 128, you want to move to cache memory. So again 128 by 64, 128 modulo 64, remainder is 0, right? So remainder is 0 means it can go to set 0. In set 0 already block 1 is occupied, so it will take block 0. You are getting? It will take block 0, right? Next 129. So again when you perform modulo division on 129 with 64, you will get 1. So the result is set 1. Okay, again that means the block 129 of main memory can go to set 1. In set 1 it can take any block. Are you getting? So in set 1 there are 2 blocks, block 2 is already occupied, so it will take block 3, right? So this is the overall logic. Okay, so the number of blocks per set, actually there is no restriction that it should be 2 blocks or 3 blocks, or it depends. It depends on the designers of the computer hardware. So they decide, the engineers, they decide like how many blocks should be allowed per set. Okay, so this is the whole concept. So this is how it works. Okay, right? Okay, so here is so divide the cache into 64 sets. Okay, we have divided the cache into 64 sets such a way that there are 2 blocks per set. Okay, now the memory block 0, 64, 128, all these things will be mapped to set 0. In set 0 they can go to any block. In set 0 they can go either to block 0 or to block 1, that depends. Okay, and they can occupy either of the two positions, that is two blocks. Okay, fine. So again here also the memory is divided into three fields. Okay, uh, the yes, the 6-bit field determines the, there is a 6-bit field, okay, that determines the set number. There is a 6-bit field that determines the set number, okay, and the higher order 6 bits or compared with the tag. Okay, see in this diagram, actually what we are discussing in the sense, the 6-bit field determines the set number. So this I think this is not uh, this particular thing corresponds to the uh, yeah. So this corresponds to the first case, right? In direct mapping we discuss this tag, block and word. Okay, but for associative mapping, what it will become in a sense, this particular this will become this will refer to the set number. Okay, this will refer to the set number, and this will be a, for this particular case it will be a 6-bit field. Okay, so using 6-bit you can address how many locations, 64 locations, 64 location. Okay, so it will refer to actually which set you are in, which set that particular block of the main memory will be available, right? So that will be represented through the 6-bit. Okay, so that is what the 6-bit represent. The 6-bit field determines the set number. Okay, the middle 6-bit, and then also there will be another 6-bit, the higher order 6-bit. Okay, the higher order 6-bit that will identify in that particular set, again in a given set, again in every set you have two blocks. For example, if the set number maps to the one particular set, right? Again this set contains two blocks, right? Out of this it maps to which block, out of this it maps to which block, that will be identified by this tag. Okay, to locate the set you use this set number, this 6-bit field, and then using this tag field, this tag field should be compared with both the blocks available in that particular set, to whichever the block the tag, to whichever the block the tag bit matches. So that is that particular block which you are searching for. Okay, and the lower order 4-bit, as usual, it refers to a particular word in a block. Okay, each block contains 16 words. To refer to the individual words we use the lower order 4 bits. Okay, right? So this is how the concept of set associative mapping works. Okay, but there is no hard and fast rules that, okay, here, so this diagram, this is not this is the correct one. Okay, this is set number, this should be set, this should be 6, and this also is 6. Okay, but there is no hard and fast rules that the set should have only 2 blocks. Set can have any number of blocks. Okay, for example, say that we form a set of 4 blocks. If you form a set of 4 blocks, if 4 blocks form a set, okay, in that case what will happen, when 2 blocks form a set, the number of sets were what, previously 128 blocks. Okay, so two blocks becomes a set, so we divided 128 by 2, so totally there are 64 sets. Okay, if 4 blocks form a set, then it is 128 by 4. 128 by 4 is what, 32. Okay, for 32 then you need how many bits, then in that case here 5 bit is enough. In that case this will become 5 bit. Okay, right, and this will become 7 bits. Are you getting? This will become 7 bits. Okay, so, or say for example we want to form say 8 bits, I mean 8 blocks, we want to make 8 blocks to one set, 8 blocks to one set, so then 128 by 8, divide 128 by 8. So if you divide 128 by 8, there will be totally 16 sets. Okay, there will be totally 16 set. If it is 16 set, then to refer the set number, to refer the specific set, we need only 4 bits. Okay, we need only 4 bits. In that case, the rest of the 10 bits will go for the tag number. Okay, 10 or 8 bits. 8 plus 4 12, 12 plus 4 16, 8 bits, right? Are you getting? So this is how it works, right? So the number of the number of blocks per set is actually, it is something which to be decided by the designer, right? Okay, right. So as we have already discussed, set associative mapping, actually it is a combination of direct mapping and associative mapping. You may ask how it is a combination of both. Okay, for example, let us assume that all the blocks are in one set. All the blocks are in one set. What does it mean? Say in the previous case, we have discussed that if 4 blocks form a set, eight blocks form a set, like that you can keep on increasing, like, right? 16 blocks form a set. Okay, so let us do that. So up to 8 we have went on, right? So if it is 16 blocks is equal to a set, then it will be 258 by 16. Then how many sets will be there? Sorry, 250, totally 128, right? 128 by 128. If 16 blocks form a set, so it is 128 by 16. 128 by 16, there will be only 8 blocks. To refer 8 blocks, it is enough just to have 2 bits. Okay, like that you can keep on increase. You can keep on increase. Say that all the one, say that one block, one set contains 128 blocks. Okay, in this case, one set is equal to 2 blocks. One set is equal to 2 blocks. Okay, if one set is equal to 128 blocks, if one set is equal to 128 blocks, okay, right, then in that case our cache memory can have how many set? In that case our cache memory can have how many sets? It can have only one set. It can have only one set. Okay, so and what will you give that set number? Set number 0. There is no number 0. Okay, there, or you can say just 0. Okay, then you need how many bits to refer to this set? You don't need any bit at all. You don't need any bit at all to refer to this particular set. Okay, in that case your memory addressing will be 16 bits. Out of all the 16 bits, first 4 bit will be, the least significant 4 bits will be used to address that particular, least significant 4 bits will be used to address the particular word, and the rest of the 12 bits you will be used to identify the particular block number, will be used to identify the particular block number. So this is equal to what? This is equal to associative mapping. This is what associative mapping we did, right? So if all the blocks are kept in one set, if all the blocks are kept in one set, then that is called as fully associative mapping. That's what we have discussed, right? And so this is one extreme case. Another extreme case is 1 block per set. 1 block per set. Okay, assume that for per set we have 1 block. Okay, that is, here we assumed one set is equal to 2 blocks, but let us assume one set is equal to 1 block. One set is equal to 1 block. Okay, then you have how many sets? Then you have 128 sets. Then you have 128 sets. Okay, right? Then to refer to 128 sets, you need how many bits? You need 7 bits. You need 7 bits. Okay, but the cache can have only 128 blocks. So which combination of 128 blocks is available in the cache? For that we need a tag bit of 5. Okay, so this is nothing but what? This way of mapping is nothing but direct mapping. Okay, right? So set associative mapping is a generic version. It's a generic version. You can adjust it in any way. Okay, if you put all blocks together and make it as one set, then it will become full associative. Okay, if you make one block per set, then it will become direct mapping, right? Okay, so depending on the requirement, you can keep like how many blocks per set. The number of blocks per set is a design parameter which should be properly and wisely or cleverly chosen by the designer, right? Okay, fine. So So next there is something called as cache coherence. It is actually a problem of cache inconsistency. So let us discuss a little bit on that. Okay. So with each block, so we are discussing about block, right? A block is a collection of words. With each block there will be a bit associated with each block, and this bit is called as valid bit. This bit is called as valid bit. Okay. If the block is valid, it will be 1. Otherwise it will be 0. Okay. Initially when the power is given to the main memory, that is power is given in the sense, the meaning is, assume that currently the main memory, say this is main memory contains the data corresponding to process 1. Main memory contains data corresponding to process 1. Okay, right, at time t0, okay. Say later at time t1, the main memory, the some other process should come in, process p2 should come in. Okay, so process p2 should go, p1 should go out and p2 should come in. Okay, so during this time, how this p1 will be removed, in the sense some power will be given to it, some electrical power will be given to this main memory. Okay, some amount of voltage or whatever it may be. So during that time this entire cells will be cleared to 0. All these cells will be cleared to 0. Okay, it means what? The content whatever is already there is deleted, right? Now p2 will come. Okay, so p2 in the sense it's a process, it has loaded some blocks. Okay, right? So when it has loaded a new block, then the valid bit will set as 1. Okay, but when the power is given to remove p1, at that time valid bit will be set as 0. Okay, because the old content of p1 is getting invalid, right? So a block contains a valid data, then the bit is set to 1, then the valid bit will be set to 1, otherwise it will be set as 0. So the valid bit will be made 0 when the power is just turned on. Here turned on means not turning on the computer. When you want to clear off the memory, also you will give some degree of voltage. So then what will happen, whatever content will be erased out, but in spite of that you will also make the valid bit 0, which means that whatever available in the main memory in that particular block is invalid, right? Okay. When a block is just loaded into the cache for the first time, okay, so when the block is just loaded into the cache for the first time, then the valid bit will be set to 1. Okay, so here we are discussing in the context of cache, not with respect to main memory. Previously I am saying main memory. Okay, you let us consider it to be cache, not main memory. Okay, so the unit is a memory unit, but it's a cache memory. Okay, so whatever I said, it's applicable for cache, right? So in cache memory, when you give a power initially, it will be turned to 0. When you load the data for the first time, it will be made as 1. Okay, if the data in the cache is valid, then the valid bit will be 1. If it is invalid, then the valid bit will be 0, right? Okay, so this is our basic understanding. With this, let us try to understand what is cache coherence problem, right? Okay, see, actually there is one interesting thing is in computer is the main memory can be updated. See, this is quite interesting. Main memory can be updated by some source bypassing the cache memory. There are some sources which can update the main memory bypassing the cache. What does it mean? What does it mean in the sense, see, you have a CPU here, okay, and here you have the cache memory, see, this is cache, okay, and here you have the main memory, right? Okay, this is main memory. Now some content of the main memory is available in the cache memory, some blocks. Say that let us say a typical block 125. Okay, assume that this block is available in the cache memory. You know that, right? You know that this block 125 is available in the cache memory for the given time, right? Okay, and say that this 125 can be the cache memory, it has also been updated by the processor. Okay, it has also been updated by the processor, but the update has not reflected in the main memory. Okay, now the point is, see this statement, what it says in the sense, main memory block can be updated by some source bypassing the cache memory. So it is not only that, it is not only processor updating the main memory via cache, maybe somebody else can also update the main memory. Okay, what is that source? All those we'll discuss later. Okay, one such example is DMA, direct memory access, that we'll come to that later. Okay, time being, you just understand that some source can update the main memory without updating the cache memory. Some particular program or some particular hardware has that privilege. They have the right to update the main memory bypassing the cache. Okay, so in main memory, say this block 125. Okay, originally it was brought to cache. In cache itself, it is already updated. In cache itself, processor has updated this. Okay, now some other source is again updating this content in the main memory. Some other source is again updating this content in the main memory. Okay, so if such updates are happening, if some source is bypassing the cache and if it is updating that content in the main memory, then immediately you have to check whether that block is in the cache memory or not. I mean, the memory control circuit should check whether that block is in the cache memory or not. If that block is in the cache memory, then the valid bit will be set to 0. Then its valid bit will be made to 0. Why we are making it 0? Because no more this content is valid. This data becomes stale. Because already some other source has modified this in the main memory. So whatever in the main memory updated content, that will be taken as the valid content, and so what is in the cache, that should become invalid. Okay, so this should be taken care, this problem should be taken care. Okay, so this ensures that stale data will not be in cache memory. This ensures that stale data will not be in the cache memory. So the point is, there are some sources or some programs which can update the main memory bypassing the cache. In such cases, the memory control circuit should check whether that particular block is in the cache memory or not. If it is available in the cache memory, then the respective valid bit of that particular block should be set as 0. Okay, why are we doing this? Because by this we ensure that stale data or data which is invalid is not available in the cache memory. Okay, right. So that is one case. Another case is, there is something called as DMA transfer, direct memory access transfer. It means memory can be accessed without the involvement of processor. Memory can be accessed without the involvement of processor or the system bus. So that concept is called as direct memory transfer. Okay, we'll be discussing that in detail later, but here we are discussing a problem which may occur because of direct memory transfer. Okay, because of direct memory transfer, sometimes what happens in the sense, some program may copy some content directly from memory to disk. Okay, it may copy some content directly from memory to disk. Again, assume the same scenario. We have the CPU here. Okay, we have the CPU here, we have cache memory here, we have cache memory here, and here we have main memory here. Okay, main memory here, this is main memory. Say this is disk, this is disk. Okay, say a particular block is available in the main memory. Say block 124 is available in the main memory. Say block 124 is also available in the cache memory. Block 124 is also available in the cache memory. Okay, assume that CPU has already updated the block 124. Some changes has been done in block 124, and assume that the cache is following write back cache. Assume it is a write back cache. Write back cache means what? It won't update the main memory immediately. Only finally when the process is going to quit, or when there is a replacement, only during that time the main memory content will be updated. Okay, only during that time the main memory content will be updated, right? So now here what happens in the sense, because of DMA, the DMA is coming into picture, and DMA means direct memory transfer, that is memory can be accessed without the involvement of CPU and the system bus, right? So some program or some process, they want to transfer or copy this particular block 124 again from memory to disk, okay, but if it happens, okay, what's the problem in doing, you may ask. The problem is, this content is already updated by cache, and that updation is not reflected here because it's a write back cache. Okay, the updation is not reflected here. So without updation, if it was returned back to the disk, then that data will become an inconsistent data. Then that data will become a inconsistent data. That problem is called as cache coherence problem. It is called as cache coherence problem. Okay. In this case, the data in the cache may also have changed and is indicated by the dirty bit. If it is changed, it will be represented by what? Dirty bit or modified bit, which we have discussed in the last lecture. Okay. Say it is modified and it is dirty bit is set. Now the DMA wants to transfer this memory content to the disk. So the copies of the data in the cache and the main memory are different. This is called as cache coherence problem. Now how will you solve this cache coherence problem? So one of the way to solve the cache coherence problem is to force a write back before the main memory is updated. Before the main memory is updated to the disk. Okay. So before you are updating the content of the main memory to the disk, okay, before that DMA is transferring that, you have to force the memory circuitry should force and write back. Okay, because then only the updated content will come to the main memory. After that, it can be written to the disk. Right? Okay. So the problem here, what we discussed is, during DMA transfer, the memory content can be directly moved from memory to disk. Okay. But assume that already that particular block of content is available in the cache memory, and the processor has updated that content in the cache. So the dirty bit is set. Okay. Now if you allow the DMA to copy the memory content from memory to disk, then the data will be inconsistent. The data in the cache and the main memory will be different. So this problem is called as cache coherence problem. One of the option to overcome this problem is to force a write back before the main memory content is updated into the disk. Right? Okay. So that's it about the mapping functions. So basically we have discussed three mapping functions: direct, associative, and set associative mapping functions. Okay. Fine. Let us stop here. Thank you.